All right, so the next question is once again still work, energy, power. And this question is a bit of a tricky one in that they've given us a diagram. So if I have a look here, they've given me a diagram of an object, and they say this object is moving from A to B. So it's point A going to point B, and then it's moving up to a point C. Now it looks as though C is a little bit lower than point A. So there was A, and there's point B, and there's point C. They're telling me from point B up here to point A, that distance is 90 centimeters. And then they've got a point X at the bottom here, and up to, okay, my diagram is now not quite drawn to scale, where they say that is 30 centimeters. Okay, now I've got a point C, and they say from B to C, this height here is 80 centimeters. All right, the stem of the question says a ball of mass 2 kilograms. So we've got the mass of a ball, and it's 2 kilograms. So remember to put this all this information on the diagram on your information sheet, so, or on your question paper, sorry. So on your question paper, they've given you this diagram. So now read through the stem of the question, read through it, and put information onto that diagram. Or, as I say to you, what is your motto for physics? Think with your pencil. You draw a sketch on your paper, and you put all this information onto your sketch, all right? Or you do it on your question paper. So they say we've got a ball of mass 2 kilograms. It's released from rest. So the initial velocity here at point A was 0. It rolls on a curved surface, and from A to B, they're telling me it's smooth. When you see that word smooth, what is it telling me? There is no friction. All right, so immediately I know I could use mechanical energy here that we did in grade 10, all right? Because the conservation of mechanical energy can only be used if there's no friction. So just little things that you need to link the words. So when there's no friction, I can use the conservation of mechanical energy, because that is only true, is only conserved when there are no external forces, when it's isolated, when there is no friction. All right. Then it says from B to C is a rough surface. I'm just going to do it like that to show you that it's a rough surface. And that was the stem of the question. It now says ignore the effects of air resistance. And the first question was a question 7 by the looks of it. And so 7.1, it says state the principle of conservation of mechanical energy in words. All right. So the principle of the conservation of mechanical energy is what we learned in primary school, and we learned it in grade 10, so it still holds here. So it's the sum of the mechanical energy, that's the sum of your potential energy and the kinetic energy, is going to remain conserved in an isolated system. All right, so it's not a closed system. So that word closed we only use in chemistry. In physics, we use isolated, all right? So that's a very important concept here. So isolated means no matter, nothing is being exchanged. Everything is being withheld or contained in that system, all right? So let us write it down. So the principle of the conservation of mechanical energy is the total mechanical energy in an isolated system. So the total mechanical energy in an isolated, please, it's got to be isolated, very important, remains constant. So what does that actually mean? It means that the sum of the potential energy and kinetic energy remains constant in an isolated system. All right, so It means it's going to be conserved, all right, in other words. And there we go. So that is the principle of your mechanical energy. The next question says, 7.2. Use the principle of conservation of mechanical energy to calculate the speed of the ball at point B. So we want to work out the speed of the ball at point B. All right. So now, we're going from point A to point B. So what we're going to do now, we're going to work with mechanical energy. So we're going to work with the mechanical energy at A, and we're going to say it's going to be equal to the mechanical energy at B. So because we've used, so normally what you'll find is that they stagger the questions. And so what that means is that they've given us the definition for a reason. So we had to define it, and now we're going to be using it. All right, so let's have a look. So we're going to have the mechanical energy at point B. Now, if you can, please write it out in words. We don't really have a system of abbreviation for it. So mechanical energy at point A is going to equal the mechanical energy at B. Now, why are we using this? Because there is no friction. How do I know there's no friction? Because they told me it's on a smooth surface. All right? So just remember, because it's on a smooth surface, it's implied that there is no friction, and that is why I can use this. Now we're going to expand it. So it means that the potential energy plus the kinetic energy at point A equals potential energy plus kinetic energy at point B. Okay? So now we can sub in. So if you've forgotten what these equations look like, so let's just go to the info sheet. Let's just try and see if it's on this one. Yes, here it is. Let me just get a different color pen. So here is the potential energy. Potential energy, EP, is equal to mgh, where m is the mass, g is gravity, h is the height. And then if I look for EK, here is kinetic energy, and kinetic energy is equal to a half times the mass of the object times the speed squared. All right, so that is where we go. So let's go back to the question. I need to change my pen. All right, so let us have a look. So now we're going to sub in for the formulae. So EP is mgh plus a half mv squared, and that is all at point A, is equal to mgh plus a half m v squared, and that's all at point B. Now guys, what I find is the most common error here. So we do this beautifully. So we think, yes, we've got this. All right. When we sub in, what do we forget to do? We forget to square the velocity or the speed. All right, so please, please, please make sure you don't lose marks by making silly mistakes. All right, so we can do this. You've really got this. You can do this. So just remember, we don't want to lose marks for silly mistakes. So remember, when we're subbing in, be clear, what am I subbing in? It's the velocity, and it's v squared. All right, don't forget to square. Okay, so when I'm subbing in now, so what was the mass of the object? Gosh, I've forgotten already. Oh, 2 kilograms. All right. So 2 times gravity is 9,8 times the height. Now, what was the height of this object? So it's the height above the ground here. So if I wanted to, I can see it's going to be from the bottom to the top. So point A here is 30 plus 90. So that is going to be 120 centimeters. And remember, what do we do distance in? Divided by 100. Because remember, I want to convert centimeters to meters. All right. So in order to do that, I need to divide it by 100 for that conversion. Plus a half times 2. Now they told us the velocity at the top there, it fell from rest. So it's naught squared. So obviously you don't have to emphasize it like that, but there's nothing wrong with it. And you know what? I just think it's good physics. So you sub in the 0 and you square it. And I must say, science is possibly the only subject that actually gives you marks for 0. All right, so when you're subbing in that 0, a mark could be allocated. All right, so think of it like that. So sub in the 0 and don't forget to square. All right, just to keep in that you don't forget the square on the right-hand side. Okay, so let's have a look at the right-hand side. So it's 2 times 9,8. So now at point B, how high are we above the ground? So B is 30 centimeters above the ground. So it's going to be times 30 converted to meters, and there we go, plus a half times the mass times the velocity of B at point B squared. All right, don't forget the square. So that is a very common mistake. All right, so now we need a calculator. Gosh, and now it's just really calculator work. So 120 divided by 100 is going to be 1.2. So it's going to be 2 times 9.8 times 1.2, and that is going to give me 23,52. Obviously, a half times 2 times 0 squared is just going to be 0 equals, all right, so now 30 divided by 100 is going to be 0,3 times 9.8 times 2, and that's 5,88, plus a half times 2, they're going to obviously cancel, and I'm going to be left with V, velocity at B, all squared. All right, so we're going to get 23,52 minus 5,88 equals the velocity at point B, all squared. All right, so what I would suggest here is, because it's just easier, let us take VB squared to the left. So VB all squared is equal to, and you use your calculator. Please don't do it out of memory. Use the calculator, all right, to make sure you don't make fundamental errors. Minus 5.88, 17,64. Now we take the square root of that answer, and that should give us what they are looking for. All right, so we're going to take the square root of 17.64, and that is going to equal 4,2. So the velocity of the object at point B is 4,2 meters per second. And don't forget your unit. All right, and there we go. So it's really just looking at basics. So there was no friction because they told me it was on a smooth surface. So I could use the conservation of mechanical energy, where the potential energy plus the kinetic energy at one point equals the potential energy and the kinetic energy at another point. All right, so it's conserved all the way through the motion. All right, so as the potential energy was increasing, what was happening to the kinetic energy? It was increasing. All right, let us look at the next question. Now they tell us that the ball comes to rest at point C. All right, so now it's moving up the slope. All right, so I'm just going to redraw it here for us. So it's moving down the slope and it's going up. So it's moving from point B up to point C over here. All right, and here the surface is rough. So in other words, it's going to come to rest. So with that rough surface, it's coming to rest. So the final velocity is equal to 0. All right, so it's coming to rest. So the final velocity was 0. And at B here, the velocity at point B, we calculated it to be 4,2 meters per second. All right, so what are they asking us now? So they say the length of BC is 2 meters. So to go from B to C, to go from point B to point C, this was 2 meters, 2,0 meters. And there we go. it says classify air resistance as a conservative force or non-conservative force. So we did that earlier on where we said the only conservative force that you're really going to work with would be force of gravity or Fg parallel. So those are the only two that you would really work with here. So obviously air friction is going to be a non-conservative force. Okay. Then the last question says 7.4. Use energy principles only to calculate the frictional force along BC. All right, so they want us to calculate the frictional force along BC. All right, so that is the question. So looking at what we have here, I think then they're asking us in the question, so let me just write here, 7.4, they asked you to use energy principles. Now this tends to be a little bit confusing for people and they're really not sure what equations to use. All right, so maybe I can just elaborate a little bit on this. So when there is no friction, I find if you have all the information, if there's no friction, then use the conservation of mechanical energy. So use the conservation of mechanical energy. And what is that? It always starts off with EP plus EK at a point is equal to EP plus EK at another point. All right, that's when there is no friction. So always go with that. All right, no friction. Try that as your starting point. If they're asking you to use energy principles, because that's the key, is which equation do we use? There's so many on that information sheet, and that tends to get us a little bit. All right, so if there's no friction, try that. You could also use, if you wanted to, you could have used W equals F times delta X times cos theta. You could have also used that. All right, so nothing wrong with using that equation. Sorry, I've lost my page. All right, I just want to extend it. All right. Now, if there's friction, what now? Well, if there's friction, you could use, I suppose with this equation here, you could also use W net equal to F net. All right, so W net, you could have also used equals delta EK. You could have. All right, as energy. All right, but I would always go with that one first. If there's friction and you've got to use energy principles, always try to use this one first. So if they haven't specified to use the work energy theorem, which is this one, so this is the work energy theorem. So if they haven't specified it, all right, then use this one first. Use WNC equals the change in kinetic energy plus the change in potential energy. All right, I always find that this equation works out really nicely and it's really not that complicated to use. So it's almost the easier option when using energy principles is to use WNC. So the work done by non-conserved forces will be the work done by the force of friction. What force is being exposed or what is being used from B to C is the force of friction. All right, so it means then that is the only non-conserved force acting on it. In some of the previous examples, we had tension, the worker applying a force. That is a non-conserved force. And then when there's friction as well, in that equation or in that situation, WNC would be equal to the work done by the force applied by the worker plus the work done by the force of friction. But in this example, the only non-conserved force is friction. All right, so let us work with that. All right, so it's much easier. Obviously, there are other principles that you could use as well to answer the question. So always make that your first port of call. Or obviously, if they have specified to use the work energy theorem, then you would use this equation. All right, and then obviously with that, you would use W equal to F times delta X cos theta. But I just think, you know what, let's keep it simple. I really do believe in forming the KISS party. Keep it simple. All right, and science is actually straightforward. It's logical. Taking those basic principles and applying it, keep things simple. Okay, so let us have a look how we would apply it. So in this example, because there's friction, we are going to say that your work done by the non-conserved force, and in this example, it's the work done by friction, is equal to the change in the kinetic energy plus the change in the potential energy. All right. Now that equation should be on your information sheet, so let us just go double check if we see it, and there it is. All right, so let me just change the color, and here it is. All right, so it's given to you. So guys, please use it. I find that we don't always use our information sheet to its full advantage. And this is literally your crib notes. That information sheet holds so much information. So use it. All right, so let's have a look. Okay, let me just go back to the question. Okay, I just need to choose my color. All right, so let's go. All right, so here we go. So WNC equals delta EK. So this is the work done by friction. So the work done by friction is equal to delta EK. Oh, sorry, I messed that up a bit. So it's delta EK plus delta EP. Now, we're wanting to work out the force of friction. So obviously, the force of friction, we can expand that in times delta X times cos theta is equal to, now, it's going to be a half mv final squared minus a half mv initial squared. Now guys, let me just neaten this up. Let's just neaten that up a bit. So it's a half mv final squared minus a half mv initial squared plus, all right, the change in potential energy is going to be mgh final minus mgh initial. Now, I can't emphasize this enough. So this is the only place where you will make a mistake. It's the final minus the initial. So don't swap them around. All right. So when we're working out the change in kinetic energy, it's EK final minus EK initial. When I'm working out, so remember that delta symbol means the change in. So if I'm working out the change in potential energy, it's EP final minus EP initial. All right, so that is really, really important here. And if you've got those concepts, you're good to go and you'll get full marks for this question. All right, so let us sub in and then we're done. Okay, let's have a look. So we're wanting the force of friction times the distance. All right, so the distance was 2 meters. They told me BC was 2 meters times the cos. Now it's moving up the slope. All right, so if the object was moving up the slope, in which direction is friction acting? Down the slope. So what is the displacement? So that's displacement up the slope. Force of friction is acting down. So what's the angle between them? 180 degrees. That's cos of 180 is equal to a half times. What was the mass of this object? I keep forgetting. I think it was 2 kilograms. So let's just go double check. Yep, it was 2 kilograms. All right, so it's going to be 2 times the final velocity. It stopped. So it's 0 squared minus a half m. The mass is 2. What was the initial velocity? That is what we calculated at B. The initial velocity we said at B was 4,2. So just make sure you're subbing in the correct values. And what mustn't I forget? We don't forget the square. Well done. Good. Plus, so remember, work is a scalar quantity. We add. All right. Plus, okay, I'm going to do it down here. The mass was 2. Gravity is 9,8. The final height. So now this is where we need to make sure we're doing it properly. All right. So if we have a look, the change in height here. All right, it's the change in height. So it's the change. It went from, okay, let us just see what I had on the initial diagram. So it's this change in height. So here it is here, okay? So from going from C, or no, that's C was 80 centimeters, B was at 30 centimeters, sorry, so this was 30 centimeters here, all right, and it went up to 80 centimeters there. So this is going to be H final, and this was H initial. All right, so that is how you would see it. So it went up to 80 centimeters from 30 centimeters, okay? So now we'll substitute that in. So H final was 80 centimeters, so don't forget, we have to divide by 100 minus, mass was 2 times 9,8. What was the initial height? It was taken at 30 centimeters. All right, and there we go. So once we've got that, we can now go work out the force of friction. My goodness me. All right, so now this becomes a mass problem. So cos of 180 is minus 1. So this is going to be minus 2 multiplied the force of friction equals. Okay, all of that multiplied by 0 is 0 minus. Okay, so faithful calculator. Thank goodness for calculators. So it's going to be 4.2 squared. So I'm just going to go 4.2 times 4.2. Okay, multiplied by 2, multiplied by 0.5. And we get 17,64. Plus, all right, so calculator. Now we've got 80 divided by 100, so that's going to be 0.8 multiplied by 9.8 multiplied by 2. And that will give us 15,68 minus, all right, next one. So it's 30 divided by 100 multiplied by 9.8 multiplied by 2, and that gives me 5,88. So once I've got that, now we just have to simplify. Okay, so this is going to be minus 17,64, and we go to our calculator. So now we've got, 15.68 minus 5.88. 9,8, all right, and it's plus 9,8, and now we use our calculator again to simplify. Okay, let me just minimize that. I just want to extend the page. All right, so I'm sure I don't need to do it so simply that you guys know what to do, but just in case, so we'll show all the steps in between. So this is equal to minus 7,84. So I'm going to divide both sides by minus 2. So I get force of friction is equal to, you can do this in your head, but you know what? Rather just use your calculator. So obviously the minuses, the negatives will cancel. So I've got 7.84 divided by 2. And that will be the force of friction. So it's going to be 3,92 newtons.